Okay, in this video here, we're going to be talking about a library of parent functions. Sometimes you'll hear me refer to these as basic functions. And this really is in preparation for the next set of videos dealing with transformations of functions. And so these library of basic functions are very simplistic, meaning that they're things like f of x equals x, f of x equals x squared, very basic, no like multiplying or adding numbers or anything like that to them. And so we're going to look at the graphs of them, and then we're going to also look at things like the domain and range, stuff like that. So let's go ahead and get started here. I'll bring up a graph. Now the first one is a very basic function. This is the constant function. And this is represented by f of x equals c. And here, c is any real number. So the key thing here, if we were to actually plot this here, I'll just give an example. I'm not going to give it a specific number. What we end up getting is just a horizontal line. And then the y-intercept here is, of course, just c, is the y-intercept. And so one thing that's important again is that f of x equals c, it's still a function, still pass the vertical line test, but there's no x, so that's why it's just always a constant value. And then, well, what else do we want to know about this? Well, we're going to want to know domain and range. So domain, this is all real numbers. Which I'm going to start abbreviating later. I'm going to start abbreviating with a capital R here. All real numbers, this capital R with a line through it, shorthand. And then the range, remember the range is the allowable outputs, and or not the allowable outputs, it's just the outputs that we get. And so we get that this would be simply just C, because there's only one output. And then something else here is that we know that this is also an even function. And just to remind you why even functions, these are symmetric about y-axis. So that's something else we know about it. Alright, so that's pretty much all there is to that one. So let's look at the next one here. And as I said, this is going to kind of be, put the graph all the way over there. Let me move this back. Move the screen back here. There we go. So the next one here is again going to be a very basic function, and this one that we're going to look at is simply just going to be f of x equals x. Now this is actually a linear function. This is, technically it's in slope-intercept form. The slope here is 1 and the y-intercept is 0. And of course we all know what this should look like, or we should know this. It's just a straight line that goes through the origin with a slope of 1. And so this is what my graph would look like. Now you are going to need to know the graph and these properties that I'm writing down here. We will be using these in the next set of videos. Okay, here, so what do we have here? The domain, well, we can clearly see that this is defined for all real numbers. So I'll just say R. The range, so these are the y values or the outputs, and we can see, hey, I can get any output. Can I get an output of 10? Well, of course you can. You just put an input of 10 in, so on and so on. So the range here is all real numbers. And then one other thing we could say is that, well, this is increasing from negative infinity to infinity, so it's always increasing. We also know it's an odd function, which, to remind you, this means it's symmetric about the origin. And I guess we could also say that, hey, it goes through the origin, but it's pretty straightforward. Alright, so that didn't give me the thing to move. Let's try that again. There we go. So on to the next one here. And you might guess what the next one is that we're going to look at. The next one we'll look at here is f of x equals x squared. And actually I'm going to want to move that just a little bit over so I don't get the graph going through that. So f of x equals x squared. And now when we're plotting these, especially for like a parabola or for the next one we'll look at x cubed, we're going to want to have more than just 2 or 3 points plotted. I have a minimum requirement of having 5 plotted for this one here. So we do, it's got 0, 0, 1, 1, negative 1, 1, and then 2, 4, and negative 2, 4. And the reason we want to have 5 points plotted here, again, this is going to lead into our next videos when we're talking about transformations on functions. And so the shape here we know is a parabola. And so that's roughly the shape. Now, of course, we want to talk about domain and range and all that other good stuff here. So the domain of this, well, again, I can put in all real numbers, so this is just R. Now the range here, these are the outputs that I get, and one thing, you know, that we can see pretty straight away, if you have x squared, you're never going to get negative numbers. So the technical way to write this is to write it as non-negative numbers. Now, a few of you might say, well, why don't I write it as positive numbers? The reason you can't is technically 0 is not positive or negative. So you can't, you know, if you say positive numbers, you're losing the fact that it's also 0, that the output can be 0 when the input is 0. So to say all positive numbers including 0, we would say non-negative numbers. Another way you could do this is you could, of course, write f of x greater than or equal to 0, or you could put the interval notation down 0 to infinity. Except I made a mistake there because we include 0, so I'd put a square bracket here. Those would be 2 other ways you could write it. Alright, so then what else? Well, we can see clearly from the graph that it's decreasing from negative infinity to 0. It's increasing from 0 to infinity. We have a relative, which actually turns to be an absolute as well, relative min at x equals 0. And of course it is an even function, which means I won't write it down this time, but that means it's symmetric about the y-axis. Alright, so let's look at our next one. You might guess which the next one would be. The next function we're going to look at, of course, is f of x equals x cubed. And again, if we want to plot some points here, we'd have 0, 0, 1, 1, negative 1, negative 1, and then 2. Let's see here. Did I give myself enough space here? Not really. It's going to go back up into the other one here. So this is 1, 2, 3, 4, 5, 6, 7, 8. So it's actually all the way up there. And then 2, 3, 4, 5, 6, 7, 8, all the way down here. And then the whoops. That's not going through the points very well. And the graph for x cubed would look something like that. And again, I put 5 points down. Now, it's not necessary, but just to remind you, I'll go ahead and label them. This is 0, 0, 1, 1, 2, 8, negative 1, 1, negative 2, 8, negative 8, negative 1 there. Now, I don't memorize these points because, you know, x cubed or x squared, it's easy to figure these out. Just, you know, always go from negative 2 to 2 when you're doing these parent functions for x, x squared, x cubed, things like that. Okay, well, let's look at the domain and range and all that good stuff. So the domain, well, again, we can clearly see that this is all real numbers. And then also, if we look at what the outputs are, we can clearly see that I'm getting every possible number as an output. And then again, this one, like x, is increasing over the entire domain. So it's increasing from negative infinity to infinity. And we can clearly see also that this is an odd function because it's symmetric about the origin. Now, we're not going to go over any more of the x to a power, x to the fourth. Well, here, let me just kind of go up here. X to the fourth is going to simply look something like this dotted blue line that I've kind of sketched out here. It's going to have kind of a flatter bottom and then just go up quicker than the x squared is. So flatter bottom here, these parts get pulled down and then it goes up really fast. So, but it's basically still parabola-esque in shape. I mean, it's not a parabola, but it's, you know, still got a similar kind of shape going on. And then as far as like with this, if you wanted to have like x to the fifth, well, it's similar in the sense that, well, this part gets flattened out and then we go up really sharply. And then this part gets flattened out. Still goes through 1, 1, of course, and 1, negative 1, negative 1. And so if, you know, if you were wanting to draw this in a little bit more solid, x to the fifth would look something like this. But they're all kind of similar in shape. You just need to get some points there on them. All right. And as far as the properties, x to the fifth has the same properties as x cubed, x to the fourth has the same properties as x squared, so on and so on. All right, but we do have a couple more functions we're going to look at here. So let's look at the next one. The next one we're going to look at is, let's get back to red. Oh, forget it. I was trying to erase that, but that's fine, whatever. F of x equals the square root of x. Now, I'll go ahead and plot this one. I'm only going to do 3 points, which is fine. 0, 0, 1, 1, and then 4, 2. And then it's kind of half of a parabola. In fact, it's not kind of. It is half of a parabola on its side here. And so that would be square root of x. Now, of course, we can see here that the domain here, well, it's not all real numbers. This is x greater than or equal to 0 because, again, if I have negative numbers, that makes it complex. Or we could write this in interval notation as bracket 0 to infinity. The range here, well, again, seeing from the range here, I'm not getting any negative numbers, and it turns out that it is also greater than or equal to 0 for the range. And we can see that it's increasing. Now this is actually something, and again, you'll talk about increasing and decreasing. If you take calculus, you'll talk about it in more detail. And in those classes, it will be a little bit more obvious why we wouldn't include 0. It has something to deal with a concept called derivatives. And the derivative is not defined at this point 0 in square root of x. I'm not going to go into why, but because of that, we don't say that it's increasing. But that's, as I said, reserved for another course. But there is a reason why we wouldn't include 0 as far as where it's increasing. And then this has, this has no symmetry. All right. Next function here. Next function here, this is the one function that we don't plot very many points on it. F of x equals 1 over x, although we'll go ahead and plot a couple. And so we have, it goes to 1, 1, it goes to negative 1, 1, and then if you wanted to, like, do 2, this would be at a half, and then a half would be at 2, and then the same thing on the negatives. And then the graph is going to look something like this, which you're probably familiar with, or if not, you'll see it now. So it looks something like this. And of course here we can see clearly, just even from the function, that it doesn't have a domain of all real numbers. It's got, the domain is all real numbers except if I could spell this right, I'm having problems spelling again today, except x equals 0. And actually, if you think about the range here, similarly, it's the same thing. You're never going to get 0 out of this, even if you put a really big number in there. For instance, like, 10 is not that big. A million. 1 over a million is still not 0. It's a really small number, but it's not 0. So this is all r except f at x equals 0. It turns out that this is an odd function. And it's decreasing. Where is it decreasing? Well, it's decreasing from negative infinity to 0, along with 0 to infinity. Now, you couldn't just say negative infinity to infinity because it doesn't include 0. Alright, we got one more function and graph that we're going to look at. And this might be new to some of you. And the notation changes from depending on what book you're looking at. The notation for this particular function can be different. So let's look at what we have, and I'll give you also some of the other notations as well. So we have f at x equals, and then you do a double square bracket x. And this is actually equal to the greatest integer less than or equal to, come on, to x. So some examples here. If you're looking at f at 3.2, this would simply be equal to 3. Similarly, if you do f at 3.8, this is equal to double square bracket 3.8, which is still also equal to 3. Now, some people want to say, oh, you're just truncating the decimal. That's not a good way to think about it. You want to think about this as rounding down. Another name for this function is actually something called the floor function. And in programming, this is actually used quite a bit, and it's actually a function that often is just called floor function. And again, this is rounding down. Now, the other way to see this notation, so we have double square bracket. Sometimes you'll see it as, looks like an L and a backwards L, encapsulating the x. that is another notation that is used. Now, before we look at the graph of this, you could look at f at negative 1.2. And positive numbers people typically do okay with. It's the negative numbers that people mess up on. And this is why I say thinking of it just as truncating a decimal is wrong, because if you truncate the decimal here, you get -1, but that's the wrong answer. You want to think about rounding down. And if you're rounding down, you're thinking what number to the left, or not number, what integer to the left is -1.2. And the integer to the left of -1.2, of course, is 2. So this is equal to -2. And when we look at the graph here, we'll quickly be able to see that. Okay, so let's go ahead and look at the graph now that I mention it. Alright, there we go. Okay, so what would this graph be here? Well, if I started, I mean, it doesn't matter where we start. So we'll start, like, let's go ahead and start at the 3 here. So let's go ahead and 1, 2, 3, 4. So if we have 3, well, there's nothing to round down, so 3 would just be at 3. And then we said all the, like 3.8 and everything, all of those round down to 3 until you get up to 4. Now at 4, we would jump up to the number 4 and have the same kind of thing. And so now just kind of continuing this pattern, we can fill in the rest of the graph here. And so on and so on. And you can clearly see here with the negative numbers why -1.2, which would maybe be like right about there, rounds down to -2. Alright, so let's look at domain and range here. So the domain is all real numbers. The range now is not all real numbers, but it's all integers. Okay, one last thing here in this video. Sometimes this is not covered in all math textbooks, but I think it's important since we've talked about this greatest integer less than or equal to x, or this floor function. There is also, if you have a floor function, you might guess there is also something called a ceiling function. And the ceiling function is denoted as f at x equals, now the domain and range of the ceiling function is the same as the floor function, but this one you want to think of it as just you round up. So again, if we thought of it as the ceiling of 3.2, the ceiling of 3.2 would be 4. The ceiling of 3.8 would be 4. And then the ceiling of a negative number, for instance, -1.2, well, you're rounding up, so you're going to the right, so this would be -1. So ceiling function is also something that's used in programming quite a bit as well. Alright, so this wraps up our parent functions here. Next video is we're going to be looking at transformations of functions.